some cases, some things might obstruct any of these processes. For example, we might not be able to get a sample. Well, that's bad news. Or we might get a sample, but we might not be able to make inferences back to the population. Maybe the way we fetch the sample from a population was not in a way that will allow us to make that inferences. So you can only do this step, the inference step, if the sampling step was done correctly. You can sample in a way that is non-probabilistic and somehow expect that you'd be able to make inferences from a sample to the population. So again, it's very important that we ensure that the way we sample is valid, because that is the only scenario in which we'll be able to make inferences from a sample to the population. Now, again, in some instances, we might have problems with sampling. Maybe we sampled in a way that the sample we've fetched is not necessarily representative of the population. Now, that is where weights come in. The whole idea behind weight is we want to complete this cycle of inference. We want to get, data from the population to get the sample, and from the sample, we want to make inferences to the population. But for whatever reason, this step was not appropriate, right? So the whole process of weight is, how do we then mathematically or statistically ensure that we can still complete this step, even though this step was defective for whatever reason? And so that's the whole idea. That's the whole lecture in 1 second. The process of ensuring that we can somehow force the sample to resemble the parent population so that we can make inferences from the sample to the population. Now, there are two similar terms that we need to make sure we understand. There's some background. Lungile, I'm not sure what is the source of that background noise. Please, can you mute everyone? All right, so there are two terms that we want to make sure that we're clear in what they mean, because they're similar but very distinct. The first term is standardization, and the second one is weighting. And so they're similar in their, at least philosophically, in what they attempt to do, but they are very different in the practical use cases. So let's explain what those two terms mean. In standardization, we have two populations here. Oops. We have two populations, population 1 and population 2. And we want to compare these two populations. But obviously, they are like apples and oranges. The shape of these two things are not the same. We can only compare two things that look alike. So in this case, you have this round bowl and with this clay that is very amorphous. And here you have this cylinder or this rectangular block of clay. They are different in their shape and their size, so we can't compare them directly. So in the real world, standardization is when you have two populations that are so different, but you want to compare them. So let's say that I want to compare, let's say, death rates between the US and, let's say, Nigeria. Well, the problem is that the US is largely an elderly population. Nigeria is largely a youth population. Of course, you expect the death rate in an older population to be higher. Well, because they're old. You expect the death rate to be smaller in the younger population because they're young. So you can't directly compare those two things together. It's like comparing apples and oranges. But when we need to compare them, what then do we do? Well, that's where standardization comes in. So standardization allows us to pick a reference population, and then we force that population, those two populations, to look like the reference population. So this was the original shape of this clay, and this was the original shape of this population too. But with standardization, what we're doing is that we take population 1 and we force it to look like the reference population. And we take population 2 and we also force it to look like the reference population. Now, they look alike and we can compare them, right? So that's essentially what we do in standardization. The reference population can be another population altogether. So if we're comparing, for example, Nigeria and the United States, the reference population could be, let's say, the UK. We can say, what if Nigeria had the same distribution of age like the UK, and the US too had the same age distribution like the UK? So in this case, the UK is serving as a reference population, and we are forcing the two populations to resemble the UK in age distributions. But we can also use either population as a reference population. We can say, what if the US had the age distribution that it currently has, and then Nigeria also had the age distribution of the US that it currently has, what would the death rates be like? So the bottom line is that with standardization, we're trying to force the two populations that are different to look alike in the particular parameter so that we can compare them and know that we're comparing apples to apples and not apples to oranges. That's what happens in standardization. Now in weight, it's a bit different. So in weight, we have two things. Again, let's go back to our cycle of inference. We have a population and we have a sample. Those are the two things that we're trying to compare in terms of making inferences from the sample to the population. So here, this is our sample, and this is our parent population. So this is what the population looks like. So this is, for example, we're saying that the age distribution of a population looks like this, and the income distribution looks like this. So this is the shape of the parent population. This is the shape of the sample. These two guys are nowhere alike. So this is a problem for us because going back to the cycle of inference, we can't make inferences from the sample to the parent population if the sample does not look like the parent. So, well, what do we do? Well, we can then force this sample to look like the parent population, right? Now, it looks like the parent population is not exactly like the parent population. So that's what we call a pseudo population. So this is essentially what weighting is all about. Weights, when we apply weight or when we create weight, it's just a process of, we take this lump of clay, the way it is, and we force it to look like the parent population so that now we can now make inferences from that sample to the parent population. So it's a whole bunch of statistics and math, but in simple terms, that's what we're essentially trying to do. We're trying to force the sample to look like the parent population. It's never going to be exactly like the parent population, but it looks close enough that we can make our comparisons or make our inferences from the sample to the parent population so that ultimately we achieve this. This is all we're trying to achieve, that from the sample, we can make inferences to the parent population. And so, but for that to happen, the sample has to be representative of the population. That's lookalike. All right. So this is the same thing explained a different way. So assume that this is the parent population here. So here we have three segments of a population, the blue, the orange, and the gray. Scenario one, we have a sample that is not biased. Of course, the sample is smaller than the population, as we would expect. So this cycle is smaller than this bigger cycle, but every other thing looks exactly like the same. So the distribution of blue is exactly like the way it is here. The distribution of the orange is exactly like the same here, and the same thing with the gray. In this case, we don't need weight. There is no need for weight because the sample already looks like the parent population in terms of its distribution. So weights are not needed here. Now, scenario B, which is the red arrow here, we have, again, a sample, but here things are a bit different. We can see the distributions of this red, orange, blue, and gray do not reflect the original population from which it came from. So here you can see that the blue is more than half here, but it's just a smaller fraction here. And here the gray is much smaller in the parent population, but it's much larger here. This is not good. We cannot make inferences from this to this because it doesn't look like the parent population. So what do? Well, we use weight. We use the weights to force the sample to now look like the parent population so that now we can make inferences from the sample back to the parent population. And so our cycle of inference is maintained. From the parent population, we got a sample. Well, it had a K-leg, but we corrected that K-leg with weights. And then from the weighted sample, we can now make inferences back to the parent population. So again, that's just all we're doing with weights. This is, again, the same thing in a different way. We're saying the exact same thing. So we have a target population that gives rise to the sample population. And sometimes the sample population, we might have, for whatever reason, the analyzed population, our data set may not even look like the sampled population, which may not look like the target population, right? And so weights or weighting is a process that allows us to ensure that the data set you have on your computer, that when you analyze it, you can make inferences that can be extrapolated down to the target population. So the choice of sampling affects how all of these things go, right? Again, if you've attended our previous class on sampling, we said the very first question you ask when you're doing sampling is, do I have a sampling frame that is complete, correct, and current? Remember, we'll talk about the 3 C's. The sampling frame has to be correct, it has to be current, and it has to be complete. If you have a sampling frame that meets those characteristics, then you can do a simple random sample. If you don't, then you have to do a cluster sample or a stratified sample. And so sometimes the choice of sampling is dictated for you, and the choice has implications. So it is not enough for you to just know that, okay, this is simple random sample. You need to know that whatever choice you make has consequences, and that you might need to do some extra work after you collect data to make sure that you can make the correct inferences. Again, simple random sample. We have a population, and we draw a random sample from that to give us the population we're analyzing, or the sample population. When we have disproportionate sampling, we have a scenario whereby the different strata in our population are not represented in the correct way within our sample. So here we have 4 strata: green, blue, brown, and black individuals. And let's take just the brown ones, for example. The brown individuals make up 21% of the parent population, but make up 31.5% of the sample population. So we only have proportionate sampling if the percentage in the population is exactly the same as the population in the sample. So if the brown people were 21% in the parent population, then they should be 21% in the sample as well. If that is not met, then we say we have disproportionate sampling. And so when you talk about errors that could arise in survey design, we always categorize them into 2 big buckets. We talk about sampling errors and non-sampling errors. So non-sampling errors are errors that have to do with questionnaire design, or interviewer bias, and all of that. It has nothing to do with sampling. But then we'll talk about sampling errors. These are errors that have to do with how the frame was created. Remember, a frame or sampling frame is a spreadsheet that has all the names of the items you want to sample. Again, remember the 3 C's. The sampling frame must be complete, correct, and current. If any of those are not met, then you have frame errors. But then you also have non-response bias, which could also be a major source of error in sampling. Let's illustrate it this way. So here we have 3 pots, all right? The pot itself is our population. The cover is a sample. This is an ideal case, right? The cover of a pot fits perfectly on the pot itself, right? In other words, we're saying that the distribution of whatever group in the sample is exactly equal to the distribution in the population from which it came. So that is proportionate. It's fine. In this case, we don't need to do anything because life is good in this kind of scenario. When you do a simple random sample, you hope that this is what you get, right? That the distributions are the same. Of course, that is not always met, but this is the yardstick against which we want to understand these other 2 scenarios. Now, here you have the population here, which is this size, the size of a pod, and then you have the sample. In this case, the sample is much smaller. The distribution of this population is much smaller in the sample than it is in the population from which it came. So let's say in the overall population, let's say we're talking about whites. Whites make up, let's say, 71% of the population. But in our sample, they were represented, maybe they were just 30%, right? Or let's say you are doing a survey in South Africa where Blacks make up about 60% of the population, but in the sample, they only made up 10%. So in this case, the cover is much smaller than the pot. But again, remember that statistically, we want to make sure that we always get back to this scenario. The pot and the cover must be exactly the same. So if the cover of the pot is too small, we have to add weight to expand it, to make it bigger, right? So intuitively, you have to know when, in a case where the weight will be big or when weight will be small, right? In this case, the cover is much smaller. We need to make it bigger, obviously. That means that this population will have larger weight in the analysis, right? And so just by looking at the population, you should be able to tell immediately that, oh, this is what the impact is going to have on the weight. Here you have the opposite. You have the population here, and the representation of its population is much bigger or much larger in the sample than it is in the population from which it came. So that is the reverse of the scenario we mentioned earlier. So let's say you have whites. Whites make up 10% of the South African population, but in your web survey, there were like 60%. Maybe you went to an affluent neighborhood to collect your data, and most of the participants were whites, right? Well, in this case, the representation of whites in the sample is much bigger than in the population. So you have a scenario like this. So you should intuitively know that the cover is big. We got to make it smaller so it fits the pot, so that the weights, in this case, the whites will have a smaller weight because they are overrepresented in the sample, right? So again, these are all the things we're trying to achieve when we calculate weight. This is the exact same thing said in a different way. We have this line that represents if the sample's distribution is exactly equal to the population's distribution. So if we're at 21% in the population and 21% in the sample, then the individuals are this line, right? So the further away you are from this line, the more weight we have to add to you to make sure you get to that line, right? Because the goal eventually is to make sure that our samples distributions are similar to that of a population from which they came. You cannot have a weight of 0. So let's just establish some basic rules that you have to be aware of. Weights cannot be 0. Weights cannot be negative. A weight of 0 simply means that that individual does not exist. So weights must be positive values and non-zero. So this is just a snapshot, a screenshot of a data set, a National Youth Tobacco Survey. And we want to test our knowledge of what weights mean just intuitively. So you have this data set here, you have some variables, but this is just the variable we want to focus on here. The fin weight, FINWGT, final weight. So individual number 1 has a weight of approximately 4. Individual number 15, or let's say number 14, had a weight of approximately 3,000. What does that mean intuitively? Who can explain that to us? So the first guy has a weight of 4, then the next guy has a weight of 3,000. The first guy, the population from which he came, compared to this second guy, was this one oversampled? Which group was oversampled more? So I want to hear your thoughts. So there are 2 questions here. First of all, what does the weight of 4 mean? Just intuitively, how would you explain that to your grandmother? A weight of 4 or a weight of 1,300, what does that mean in just simple lay terms? No technical explanation, nothing, just simple intuitive meaning of that. What does it mean? You can unmute and answer if you want. Let me see, or you can type your answer in the chat box. So first of all, let's just focus on the meaning. What does it mean? The weight of 4, what does it mean? I see somebody says the child. No.
Is a count.
A count, yes. What does it mean? So how will you explain that to your grandmother?
That means there's a value of 4.
Okay.
That means four entity.
Okay. 4 entities of what? Like, what does it mean?
Comparatively, it means the 4 is overrepresented compared with the 3,000.
Okay. For now, we're not talking. Let's leave comparatively. Let's just look at the absolute value of that number, right? What does 4 mean? I see.
Please, can I speak?
Please go ahead. Yes, Theophilus. Yes.
Okay. So the value of 4 means that that particular individual or that sample is more closer to the population or more represented to the population than that of the 3,000.
Okay.
And no, it means for every 4 4 individuals in that population, 1 individual is choosing to represent that population.
Excellent. Excellent. And so Ahmed Dahiru makes a good point here in the chat. He says, it means, I'm just reading out what he says. It means that there are 4 other people like that person in the actual population. So, well, it's not 4 other people. It means that that guy represents 4 people, including himself, right? So that means that a weight of 4 means that you are standing for 4 people, including yourself. A weight of 3,000 means that you are representing, think of it in the context of politics, right? When you have like a local government chairman, that chairman is supposed to represent everybody in his constituency. So think of it in the context of constituents or constituencies. A weight of 4 means that, oh, this is a constituent of 4. Like that guy represents 4 people like him, including himself. The guy that has a weight of 3,000 means that he has a larger constituent, right? He's representing 3,000 people, including himself. So the answers on the chart that says, oh, he's a child, you are thinking of it like a literal weight. So we're not referring to physical weight. Just to be clear, we're not talking about kilograms or grams or pounds. We're talking about just weights do not have a value. They are unitless, right? All right, so now that we know this, now that we know the absolute meaning, now let's talk about relative. Now, if you don't know anything about the population, we don't know anything about this population, but just from basic statistical knowledge, the guy that has a weight of 4 and the guy that has a weight of 3,000, what inference can you make? Again, think back to the illustration of the pots on the cover we talked about. That when do we have to make the weights big? And when do we have to make the weights, when are the weights smaller and when are the weights bigger? So the guy with the 3,000 weight, right? Let's go back to the pots, our pots here. Which scenario best represents that guy, the guy with the weight of 3,000? Is it pot 1, 2, or 3?
The third pot.
Pot 3.
Really?
No, the second pot, because he's underrepresented.
Exactly.
So the weight needs to be higher.
Exactly. So remember that when we are adding, the whole point is that the pots and the covers must be the same size, right? So if the cover is much, much smaller than the pot, we have to add more weight to make it bigger. That should fit the pot. It must fit the pot, right? So, so if somebody comes with a very, very huge weight, you're like, oh, you should know automatically, wow, this population you came from was surely underrepresented. The cover is so small that we have to add so much weight to make it big. Are we all good? So you should understand it intuitively. I mean, and so in the population, that means that the sum of all the weights equals what? Who can deduce from that? If you add up all the weights, what does that give you?
The weight of the population, 100%.
The weight of a population, I want another word.
1.
Not 1. It gives the total size of a population.
What do you mean by this?
The 100% of the population.
Mr. Just
Make 100%.
Finale, can you kindly mute yourself? Longley, can you kindly mute everyone, please? All right. So when we add up all the weight together, that gives us the total population size. Now, you also have some things we have to concern ourselves about. Today's session is about weight, but I mean, it won't be appropriate to talk about weight without at least mentioning 2 other variables that you need to be concerned about when you're analyzing complex data. This is the PSU and the straton. The PSU stands for primary sampling units. Primary sampling unit simply means it's the first stage of sampling when we're doing cluster sampling. So imagine that we come to a country to do a national survey of students. So the way we're sampling is that we, first stage, we go to schools, and then we select certain schools. Then within those schools that were selected, we select classrooms. And then within those classrooms, we select all the students. Well, the first stage was the school. And so because the first stage is the school, we call that the primary sampling unit. So you only have PSUs when you have cluster sampling. So that is something you should also know intuitively that, well, if somebody's talking about PSUs, that means that there's cluster sampling going on. And then you also have stratum. Stratum occurs when you have stratification, right? So let's visualize it. We've talked about this several times in our past classes, but let's just again visualize it here. Clusters and strata sound similar, but they're very different. These are strata. These are clusters. Strata, within each stratum, everybody looks the same within a stratum. So in large surveys, for example, in the US, we always want to make sure that we capture certain groups, like minority groups. So we would say, all right, we want to make sure that there's adequate representation for Hispanics and for Blacks. These are minority groups. So within that stratification means that we'll identify counties that are predominantly Black, and we'll set them separate. And we'll identify counties that are predominantly Hispanic, and we'll set them separate, and then the rest. So that means that we make sure that we sample from those clusters that we have defined. So the whole point of stratification is to make sure that you make certain groups that you're interested in are well represented. That's why you do stratification. And then clustering is done to, ensure efficiency. Like we mentioned earlier, when you don't have a complete sampling frame, then you use cluster sampling because it doesn't require you to have a list of everybody in the population. All right, so again, our focus is on weights, but I just mentioned that so that we have at least that in the back of our mind. We'll have future sessions where we'll go into deeper dive on stratifications and clusters, but for now, that should suffice. So again, PSU stands for primary sampling units, and it's primary because it's the first stage. Talk about primary school and talk about primary teeth. Primary in that context always means first stage. So primary teeth means first stage. You have primary, there's always secondary. So primary sampling units, you have secondary sampling units, which is the second stage. You will have tertiary sampling units, which is the third stage. But bottom line, what we're trying to emphasize is that whenever you have PSUs, that's because you have cluster sampling. When you're analyzing complex survey data, you cannot delete rows. I cannot emphasize that enough. And we've covered this in past classes, but I'm sure there's some new people here. So some of these things, I'm just repeating them to make sure that those who are new also understand the context. So whenever you're analyzing surveys with weight, we do not delete rows. The reason is because whenever we're trying to do a subgroup analysis, the analysis must be done, the mean estimate must be calculated only among that group, but the estimates of a variance must be calculated among the whole population. So let me explain what I mean. So in this data set, we have 2 boys and 2 girls. We want to do analysis only among boys. This is the wrong way to do it. In this approach here, this guy has now deleted the rows for girls. So he only has two rows for boys, and he has analyzed the rows that he wants. Now, you have a problem on your hands here. The mean estimate will be correct because the mean estimate is only calculated among the rows of interest. So in this case, we're interested in boys only. So the mean is always calculated only among the rows of interest. However, when we are doing analysis of complex data, the variance, which is the confidence interval, must be calculated from the whole population, right? So even though you are restricting your analysis to only boys, the mean will be calculated from only the first 2 rows, but the confidence intervals must be calculated from all the rows. When you delete the rows that are not wanted, what you've done essentially is that you've created error in your analysis, right? So what your software is doing in the background is that it sets the value of the weight to 0 for the subgroup you do not want, but it maintains the PSU and the stratum variables. And again, we're going to cover this in more details in future sessions, but I just want us to make sure that we establish some cardinal rules when we're analyzing complex data. The first rule we said was that you cannot have a weight of 0. The second rule is that you cannot delete rows. Don't drop rows, delete rows, or anything like that when you're analyzing complex data, because you need to use a special software that accounts for the complex design. So that's just to emphasize all of that. The third rule of thumb is that once you analyze complex data, we no longer refer to the population or the sample. Again, remember the cycle of inference. We get a sample from the population, and we'll make inferences from the sample back to the population. So the point of what I'm saying is that once you weight data, you have to stop using the word sample immediately. The word cannot appear in your results anymore, right? You now have to refer to the population. Here, for example, let's look at this MMWR from CDC. So here it says, this report provides the most recent national estimates of smoking prevalence among adults aged 18 years or older based on data from the 2012 National Health Information Survey. That survey included about maybe a few thousand adults in the US. Now, pay very close attention to how we interpret the results. In 2012, an estimated 18.1% of US adults, take note of that. We didn't say 18.1% of the sample. No. We said 18.1% of all American adults. Why? Because we have weighted the data. And so we cannot, at this point, once data are weighted, we automatically stop saying the sample, because now the inferences have been made to the general population, right? It should also be very clear to you how we got this number, 42.1 million, right? All we simply did is take the sum of all the weights for people who said they were smokers. If you add all the weights, it will give you 42.1 million. So again, repeating this just to make you understand how we analyze complex data and how we get some of these numbers. You should be able to understand at this point that when you just sum the weights for any subgroup, that gives you the actual number in the population of interest. And that once you weight data, we immediately stop referring to the sample. We now make reference to the population, right? So again, going back to our cycle of inference, because that is the most important slide. So again, this one here. So once we weight the data, we completely ignore this guy from going forward. All our inferences are based on this population. So of course, we took out just a small sample to generate the weights for smoking prevalence. But once the data are weighted, we stop referring to sample. We say 18.1% of American adults, not 18.1% of the sample. Why do we care about the sample? We don't care about the sample now because we've already weighted the data. So again, this is just to again emphasize why we weight data and what it does and how it changes the way we make inferences and the way we communicate our results going forward. All right. Now you have to make sure you do it correctly. You see a lot of papers that analyze survey data and then they just pretend as if the weights were not there. That is, I cannot emphasize enough how wrong that is. You know, at the very least, you'll have to issue an erratum for such kind of, blatant errors. This paper, for example, they said, oh, following the publication of our article, we noticed we had not considered sampling weights. Okay, oh, really? Okay, well, so you have to read the documentation. When you pick a data set, especially when you're using publicly available data sets, you want to read the documentation to make sure that you have accounted for weights. We've had several classes on analysis of weighted data. We're going to have future sessions. So for those of you who have no clue how to analyze complex survey data, just make sure you follow us on LinkedIn so that when we announce such classes, you can sign up. All right. This is just to tell you the implications of ignoring weights. This is what happens when there are weights in your survey, but you choose to ignore them. Well, maybe you didn't choose to ignore them, but whether knowingly or unknowingly, you ignored them. So here, this is the outcome of interest, column 1, and we want to apply weighted analysis because weights exist. Oops, sorry. So the analysis will simply be 1 times 10 plus 2 times 100 plus 3 times 1 plus 4 times 10 plus 5 times 1,000 divided by the sum of the weights. Well, that's essentially what your software is doing when you take a column and take the mean, the weighted mean. That's exactly what it's doing. And so here, you can see that the mean is 4.7. when you fail to account for weight, what you are telling the software is that everybody has a weight of 1. So an unweighted analysis is equivalent to a weighted analysis where everybody has a weight of 1. So you are assuming that the weights are equal for everybody. That's what we call a self-weighted analysis, right? So that's what you're assuming implicitly, whether you know it or not. So here, the analysis is simply 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1 plus 5 times 1 divided by the sum of the weights. So you see the result here is 3.0, but here is 4.7. Obviously, 4.7 is not the same as 3.0. So your results are deeply flawed. This is just a toy data set. So here the results may not look so drastically different, but yeah, you cannot take a survey that is complex, that has weights, and just ignore the weight. That is so wrong. And so when we have our sessions on weights, we'll talk about how that is done. And so we've already covered what weights are and what the interpretations are. Now let's just talk about 2 types of weights. Design weights and non-response weights. We use design weights, as the name implies. Design weights are weights that are indicated by design. So we designed the survey a particular way, and so we are aware that we have intentionally injected bias, but all by design. So let's go back to the example we gave earlier. When you want to oversample groups, I want to make sure that there are enough Hispanics and Blacks in my survey. So I intentionally oversample them, right? So in that case, that's the scenario where we have a pot that is too big. The cover is big because the representation of those individuals in my survey is much bigger than it is in the parent population. Well, since that was by design, I have to make sure, and that's not a problem, right? We have ended up with bias. As far as the pot and the pot cover are not the same in size, that means there's bias. It means there's selection bias, right? But that selection bias is by design. Is to make sure that I have enough people in my survey. Well, and that's not a problem. It's only a problem when you do that and now you forget the second part, which is to create weights that will adjust for the bias that you intentionally injected by design. So again, we want to have enough people in our survey. That's all fine and good, no problem with that. But when you do that, you also have to make sure that at the end of the day, you create weights that will adjust for that bias that we intentionally injected by design. So that's what design weights is all about. We have a cover that is too big by design, and we want to make sure that the cover matches the pot perfectly, and we'll do that by weights. So that's design weights. Now, non-response weights they're not by design, right? So the 2 types of weights, non-response weights and design weights, one is we, the designer, we, the investigators, created the error. The other one is not us, it's the respondent's fault, right? They refuse to respond. That's why it's called non-response, right? So one is from the issue is from us, the other one, the issue is from the respondents. Right? But either way, we have bias. So in this case, the respondent refused to participate in the survey, right? So in this case, the pot's cover is still small because the representation of individuals is much smaller in the sample than it is in the parent population. Now, this is not through our fault. This is now the respondents just refusing to participate in the survey. So whether it was our fault or whether it was participants' fault, and I'm using the word fault in quotes, the result is still the same, meaning that the cover is too small. The representation of individuals in that particular demographic is smaller in the sample than it is in the parent population. And so we have to create weights. So sometimes we have to account for both non-response weights and base weights. We also call design weights base weights, by the way. So in that case, when we have that, we have to combine the 2 weights together. And that's, we multiplied weight 1 with weight 2. You can only have 1 weight in analysis. So when you have 2 weights, you have to multiply them together to give you the final weight. Again, you cannot have a weight of 0. I cannot emphasize that enough. So if you did your weighting algorithm and somehow you're ending up with weights of 0, well, you did it wrongly. So how do we do this? We use, this is done with, there are many procedures. The most common one we use in most large national surveys is called Raking. Raking is it's just a nickname. The technical term is iterative proportional fitting. But it's a very efficient procedure because it allows you to be able to calculate weight for multiple variables at the same time. in most of the weights you see in large surveys, we typically account for between 15 to 30 variables. We look at things like income and race and age, like some of the key social demographic variables. So it's not just looking at one variable like age and adjusting for age. No, we wait for different variables between 15 to 30 for some of the large surveys. But that's essentially what happens. And we're going to show hands-on how that is done on the Chisquares platform in a second. And so, of course, we talk about weight. We need to talk about the issues with weight too. The biggest problem with weight is that it sometimes makes the standard errors very large. So if you calculate, let's say, coefficients, you might see that, they have weighted estimates tend to have very wide confidence intervals because weights end up being very extreme in some cases. And so that's why we sometimes have to trim the weights. But of course, the problem with that is that sometimes trimming the weights is sometimes subjective. So, but if untrimmed, they end up being sometimes very large, and that could result in very inflated standard errors. All right, that's the end of our lecture. We'll proceed to do some demos to demonstrate all we've said. But I'm going to pause now before I move to demo and see if there are any questions that are outstanding. Lungi, are there any questions in the chat?
Yes, there are.
Okay.
How do you decide weight value for each data point?
You don't decide it, you calculate it. All of that. That's what the demo is about now, the next part of our lecture.
Okay, so that's the same question. Any other questions before we move? What should be perfect? What should be the perfect ratio between population and sample?
There's no perfect ratio. The goal is to make the sample look as close as again, I think I sense where the confusion is coming from. Those numbers, those weights, you're not the one who's assigning them. I think what the idea in your minds is that, I'm going to give this guy a weight of 5. That's not what happens, right? All of that is done automatically. The whole presentation is just to give you a map of what's going on, of why we need the weights and some idea so that you have some intuitive understanding of it, so that it's not that when we calculate some number from the computer, you're wondering, geez, how did we even come across this number? So the whole point is so you understand intuitively what weights are, why they work, or how they work, and why we need them.
Does weighting take away randomization?
No. The weighting corrects for insufficiencies or failures of randomization. Remember that if we selected our population at random, right? In theory, at least, we hope that our sample reflects the population because it was done at random. But sometimes we don't do things at random, right? If you have a convenient sample, look, I'm not sure why I'm re-echoing in your, if we have for example, a convenient sample, let's say, and this is what most of these news organizations like the New York Times or some of these dailies do. They get their data from on the internet. I mean, you might be browsing and then they ask you, do you want to participate in this survey about the election? Obviously, that's not a random sample. There's no probability there in selection. But when the articles are read or are written, they read, this is how it typically read. 51.1% of Americans support gun reforms. It is the inflection or the inference is made to the population. How do you think that happens? Well, they use weights. They use calibration weights to correct for the fact that there was lack of randomization. So weighting doesn't take away randomization. It is supposed to correct for failures or the absence of random selection. I hope that's clear. Okay, any other questions?
Can standard error negatively impact on the study, putting low or high weights in perspective?
Yeah, if you have a standard error, that means that you have a wide confidence interval. If you have a wide confidence interval, that means that it's very likely that you'll have overlap between two groups. And what that means just intuitively is that if the two groups overlap, it means that results that would have otherwise been statistically significant might not be significant because the confidence intervals are very wide. And because they're wide, they overlap. And because they overlap, we conclude they're not significant. So in simple terms, that's what the implications are.
At what population size can we use weight?
It has nothing to do with population size. It has to do with how was sampling done, and does the sample look like the parent population? So what you do in practice is you take your sample and you say, okay, let's tabulate this population by age and by sex and by race and by income. Now let's take the tabulations and compare them with the parent population. Okay, here my age, my data says that the 50% of or 50% of the population is male. But in the national sample, I can see that only 30% are males. 50 and 30 are not the same. This means that the sample does not look like the parent. I have to weight the data, at least adjust by age. And so that's what you do. So it has less to do with the sample. And the focus here is, let's stay on track, right? The focus is the distributions, the population makeup, the population composition. So that's what we're comparing. It's not it's the size.
Must weight be calculated in every survey?
No, it don't have to be calculated. But everything goes back to the cycle of inference. So remember we said that the first question you have to ask in study design is, what is my intention? What is the intent? If the intent is just to do a study of a sample, right, and limit our inferences to the sample, then why do we have to worry about weight? There's no need to worry about weight because our intention is to limit our inferences to the sample. So we don't care about making any inferences from the sample to the population. The problem, however, arises when our intention is to make inferences from the sample to the population. In that case, yeah, you have to worry about weight. Now, if you can't weight, then just make sure you restrict to the, to sample. So in the example I showed earlier, if with the MMW article, if we did not weight the data, or if we did not choose to weight the data, we will have said 18.1% of adults surveyed in the survey, or adults, interviewed in the survey, were smokers. So there's a difference there. We're saying 81.1% of survey participants, not 18.1% of US adults. So the result will, the major issue is how you frame the results. That's what's going to be different. The study participants versus the US adult. So again, you don't have to weight the data. It's all a question of what are your intentions.
Is it right to say interpolation of data is incorrect without weighting?
No, that is false. The interpretation of data will be incorrect if you are making inferences that are incorrect. If I said 18.1% of this sample reported they were smokers, there's nothing wrong with that. So the interpretation is only wrong when you now make this jump from this guy to this guy without considering whether this is fit for inference. That is when it's wrong. So again, it goes back to your intentions. And some of these things are questions that you would have to make the determination. You are the one who is the researcher. You're the one who has the intention. Nobody knows what's your intention. It's just between you and yourself. So you are the one who will determine whether the inference is correct or not. So it's not a question, it's an unanswerable question, really, because I don't know what your intentions are. So your intentions determine whether or not you need to use weights. But if I have a PhD student, obviously in that case, the goal of a doctoral degree is to show mastery in methodology. So in that case, even if they, it's less about the research and more about building methodology. So of course, I will require my doctoral student to, weight the data, right? In that case, because I want to see that this individual has mastered clearly certain, minimum standards. But that's a different issue altogether. But for the issue of just your inferences, well, that's your own personal decision as to how you want to make the inferences.
Yeah, I guess that also answers this question. You can refer to the population without using parent, right? That is, you can say sample and the population.
You cannot say population because that's very misleading, right? You can say, if you're referring to this guy here, you can say the sample, you can say the analyzed population. Don't just say population, put an adjective, right? The analyzed population, the sample population. Because when you say population, the first thing that comes to anybody's mind is this guy, not this guy. So make it very, if you're not weighting data, be very explicit in what your inferences have been limited to.
When tracking responses within a survey's responses towards inferences, should weights be calculated?
Well, that's the question we've been answering all this while. It depends on your intentions.
Is weight equivalent to mean?
No, it's not. We weight the data so that the means or the percentage we calculate from the results are representative. So it's not the same thing.
Can we assume it's that weighting NGOs such as UN, UNICEF use is making their estimations?
Never assume anything. Always read the methodology. Go and read the methodology that was written. So never assume anything in research.
That's all for now.
All right, great, thanks. All right, so let's go to the Chisquares platform and see how this is done. So one of the things, one of my favorite features of all on the Chisquares platform is a feature that maybe just a handful of people will ever use, and that's the weighting feature. So when you have collected data on the platform, there's the feature here that says weight data, right? Again, so the whole idea behind the weight data here is for you to apply calibration weights or non-response weights to that data set, right? Now, first things first, you can only weight, it should be obvious to you that you can only weight data when you have finished data collection. Because remember that everybody must have a weight. You cannot have missing values for weights, right? So everybody must have a weight. So imagine that you're doing a survey that is still ongoing and you decide to calculate the weight. After you finish the weight, the next guy, you have a few more responses, who will then end up having missing values for weights because you did the weight earlier. And so that's why if you try to weight the data that is still ongoing, this survey, for example, is still ongoing. If I try to weight the data to generate an error, you say weighting is only available once data collection is completed. So again, you finish your survey and then you pause the survey and then you can then generate weights. So let's now, let me look for a survey that I can pause. Let's see. Can I pause?
Asking about,
sorry, go ahead.
Sorry. Those who are asking about access to the Chisquares platform, Dr. Agaku, can you just show them how you got there?
So how I got where to this page or?
Access to the Chisquares platform. How can they access it?
Okay. To access the Chisquares platform, you can go to chisquares.com, which is the website, and then you log in. If you don't even have access to the platform at all, let me see if I can find that spreadsheet.
I'll share it.
Oh, okay, awesome. Thank you very much. All right, so like we said, your survey has to be closed. So you have to close your survey. So step number one, to generate weight, you have to close the survey first. And I already explained the reason why your survey must be closed, because generating weight means that you are done with everything. And so everybody must have a weight. You cannot have zero weight. You cannot have missing weight. And so everybody must be done. Once you're done, you come to weight data. So, so here you will come to this interface that says improve generalizability with weighted data analysis. Again, the whole point of weight is to increase the generalizability of your data, right? You don't have any weight yet. And so that's why you have this history tab shows there's no weights. So you click on new calibration weights. This is the variable name assigned by default, weight var. Again, let's go back to our slides. What we are trying to do here is to create this column. This is what we have here, right? Now, in this data set, this is a combination of both non-response and base weights. multiplied together. What we are trying to create now is just non-response weights that account for the fact that the distributions in our population and our sample population are quite different from that in the parent population. So you can assign the name here. Next, you select the variables you wish to use to weight the data on, right? Now, this is just an evaluation form, and so we don't have data on age or sex or anything. In your survey, you will have those variables. Also, it should be clear to you that if you don't have a variable in your data set, you can't weight on that data. So remember I said earlier that in large surveys, we typically weight the data on up to 30 variables: age, sex, several economic indicators, marital status, sexual orientation, and many more. But you can't weight on the data if you don't have it in your data set. That should be very obvious. So you select the variables you wish to weight the data on. This is not a very good stuff because it doesn't have any of these variables, but I'll just select and just show you for demonstration purposes. So let's say I select this, that these are the variables that I want to weight the data on, right? And I select all the variables. Just pretend that this is age and sex and race and all of those things. Those are the variables here in my data set, right? So this is this variable 1, which is this one here. Those are the categories. Now, the second thing you must do is that you have to provide the percentage in the target population. So category 1, neither agree nor disagree. Let's say that that's male. How many of them are in the population, in the target population? Now, you cannot do weighting without knowing what those numbers are. So the first thing you have to do when you're doing weight is to go and look for like a census data, right? You have to look for a source of information. And that's what I referred to in this slide here. When I said, oops. This slide here, where we talked about sources for auxiliary data or statistics for calculating non-response weight. These are in the US, these are the common sources of data we use. We use the current population survey, the American Community Survey. So, or we also use the census. So in other words, you need to find a source of data that you will get those population distributions from, right? So let's say that the census showed that the percentage of males here, or this group is 30, and the percentage here is 20, and the ones here is, let's say, 30, and the ones here is 20. You cannot put, it has to add up to 100, right? So you can, if you put something like, let's say, 99, obviously, it cannot be done because the total target percentage must add up to 100, right? So then this one has to be 20 for it to add up to 100. So that is a key thing you have to do, right? You select the variables you are waiting on. And how do you select those variables? Well, remember that we said you must tabulate all the key variables you want, and you now compare them with the distributions in your parent population. You come like age and sex and race and several indicators of socioeconomic status and marital status and so on and so forth. When you find that a particular variable's distribution is different from your parent population, then that means that you have to weight on that variable. But these are the demographic variables, right? So once we're done with that variable, that is complete. We go to the next variable, right? We do the exact same thing and so on. And that's how you do for all of them. And once you are done with all your variables, then you can create your weights, right? So what the platform does is that your data set, when you create it here, when you download your data set, you now have, when you download the raw data set or the clean data set, you will have a column that says weight, right? So in a nutshell, that's how you do non-response weight. So again, the process I showed you here is for calibration weight, also called non-response weight. So that's how it's done. Now, remember I said there are two types of weights: the base weights, also known as the design weights, as well as the non-response weights or the calibration weights. If you have the two of them together, you will have to multiply the two weights together to give you the final weight. The base weights come from the design. So when you do sampling, that's how you get base weights. So let's say I want to draw a representative sample. Can you still hear me? I'm saying I'm having internet issues. Lungi, can you still hear me?
Yes, we can.
Okay, alrighty. All right. So let's say I want to draw a representative sample. Let's quickly just demonstrate the base weight. Let's say for Nigeria, for example, and I want to, let's say, select 30 clusters from the country, and I want to sample 2,000 people. Let's quickly do that and see. All right, so here we have the selection, right? And we have the population, we have a cluster probability, the individual probability, the joint probability. Weight essentially tells us the probability of selection, right? The weight is the inverse of the selection probability. Let's, I don't like these numbers. Let's use a number that is more explicit, that is not less than. Let's use let me resample so that we can, let's say we want, hopefully, okay, I was hoping for a bigger number, but anyway, a weight in the base weight is calculated as the inverse of a probability of selection. The sampling approach used on the Chisquares platform is what we call a two-stage PPS, or a two-stage sampling with probability proportional to size. And one of the hallmarks of the two-stage PPS is that it yields a self-weighting sample. A self-weighting sample is a sample where everybody has the same probability of selection. So you can see here, the joint probability is exactly the same for everybody in this sample. The weight will be the inverse of this probability of selection. So 1 divided by this probability would be the weight. So again, to calculate weights from base sampling, you take the probability of selection and you take the inverse of that. But the sampling as done on the Chisquares platform is designed in such a way that you don't have to worry about base weight or design weight because it yields a self-weighting sample. However, you still have to worry about non-response weight because the distribution in the sample might be different. So even though you sampled individuals in a way that was supposed to be representative, participants did not respond. You did your part, but participants did not do their part, and so you still have to, worry about, non-response weight. So, in a nutshell, if you had to, let's say, use a sampling approach that was not self-weighting, let's say you have another approach you did outside the platform that resulted in differential probabilities of selection. The key word here is differential, right? Here, the probabilities of selection are not differential. They're the same. And so we have to worry, we don't have to worry about weight. We worry about weight when these probabilities of selection are differential, are different among different groups. So that's when we worry about it, right? So in that case, we'll calculate the weights from the design as the inverse of the selection probabilities. And then we will then calculate our calibration weights as we have done, as we've demonstrated. And then we'll have two weights, one weight for design and one weight for non-response. And then we'll multiply them together to give us the final weight, right? So in a nutshell, that's how weights are set up. I'm going to stop here and see if there are any questions so that we can answer them accordingly. Lungi, are there any questions in the chat, or does anyone have a burning questions from what we've explained so that we can walk it back gradually?
Yes. Okay. We'll start with Ogunboye.
Yes, thank you, Dr. Agasu. Please, I want to ask, at what point do we have to be worried about response rate? For instance, if we have a response rate of 90%, do we still have to worry about estimating the response weight for such survey?
Okay. Yes, you have to worry about response rates are useless. Responses don't tell us anything meaningful. Because what you have is that let's go with the example you said. You said that we have a response rate of 90%. It means that overall, in the whole sample, 90% of the participants you requested of overall participated in the survey. Now, that's not what we're interested in. What we're interested in is there differential response rates among subgroups, right? So, which is not answered by that question, that 90%. You can have a response rate of, let's say, because percentages are driven by the larger group. So if you have a very large group, like let's say whites in the US, for example, with a response rate of 90%, and then you have American Indians with a response rate of 20%, or you have Native Hawaiians with a response rate of, let's say, 2%. The overall response rate will still show as 90 or close to that because the large group had a high response rate, even though you have differential non-response, right? So the overall response rate is not a really good metric, So in a nutshell, yes, you still have to worry about that. And the way you can tell is not to look at the response rate by itself, but take the different groups that we've mentioned, age, sex, race, the different subgroups in your data, tabulate each of them. Now compare the tabulations you have with the distributions in your overall population. If they're very different, well, you have to be worried. Well, let me caveat that. You have to worry if you have the intention to generalize results from that sample to the parent population. If you don't care about any generalizations, then you're fine. You don't have to worry about anything. I hope that answers your question. Okay, well, I'll assume it does. Any other question?
Or he was muted.
Yeah, okay. I was muted, sir.
Okay.
Yes, sir. Thank you. That really answered my question. However, I have this another question. For instance, I'm working on breakfast or NANES data, and I have to pull out the data of I access the state, the national data, and I have to pull out the Mississippi state data or Alabama's data. At that point, how do I, because you talk about in calculation of confidence interval or variance, we should not delete any row. However, I have pulled out a particular state data from a national data. How do I go about resolving the issue of weight for such data?
Okay. So I'm going to answer specific to your use case, and then I'm going to answer in general too. So your use case, you said you're using BRFSS, the Behavioral Risk Factor Surveillance System. The BRFSS is not a national survey. Now, which is a common mistake people do when they're analyzing it. It has all the 50 US states and some of the territories, but it is not, BRFSS is not designed to yield national estimates, right? And so in your case, just taking Alabama is fine because the survey BRFSS is designed to yield estimates at the level of the states. So what that means is that the weights and the PSUs and the strata are all designed at the state level. You cannot use BRFSS for national estimates. And that's why when you look at estimates from BRFSS, so let's look at, for example, MMWR. Let me see if I can find an MMWR that has something with BRFSS. So you can see how we frame it, just to, let's see if this is. So you find that when we're reporting estimates in, let's see, let me download this issue quickly. We never report the mean for, let's see. So when you read the reports for any results from BRFSS, right? Results are never reported for the US overall, never ever. If it is reported that way, it is incorrect, right? And so you'll see that they will report things like, let me pick one sentence here. Adults with good or better health for states and territories, let's see. That's a very confusing sentence. Let me find a sentence that's just easier to geez, this is quite convoluted. This is a lot of data, by the way. So the reporting is done at the level of state. Let's look for a figure. Maybe that's going to be easier on our eyes. All right, good. Now this is much better. So age-adjusted prevalence estimates of adults age 18 years or older. So you see state on territory. Each of the states are presented. What you will never see, you see median and range. What you will never see is BRFSS presenting results for all of the US overall. That is statistically incorrect, because the best they can do is to say, we'll present for each of the states, and then we'll present the median. The reason why we're using the median and not the mean is because the survey is not designed to give national estimates. So you can think of it as a bunch of surveys for each of the different states that will just put them together, which is quite different from when we came down and sat them together at the table and we say, let's design a survey that will be representative of the country overall, right? So the way you analyze data from, let's say, the BRFSS will be quite different from how you will analyze data if it came from, let's say, NHIS, the National Health Information Survey, right? Or the tobacco use supplement, in which case it was designed to yield estimates. So in your case, all you can do is you can drop all the rows for all the other states. That is completely fine, because the survey were designed to yield estimates that were representative at the level of the states. And that's why even the way we report the data, we never ever report for the US overall, because that would be wrong, because it doesn't reflect the way the survey was designed. Does that answer your question? All right. I'll assume that does. Now, but
yes, sir. Yes, sir. Thank you.
You're welcome. Now, the extension of it is that what if the survey was designed to yield representative estimates, right? Which is it's not the question you asked, but I think it's also important to consider that part of it too. Well, in that case, let's say we take a survey like the National Adult Tobacco Survey that was designed to yield estimates both at the level of states as well as US overall. Well, in that case, you can't just drop Alabama. You can't just pick Alabama as a data set and go and analyze it as a block. No. You cannot drop. You have to analyze the whole data set. And then when you use your software like Stata or SAS or Python or R, you will specify the group you are interested in. So for example, if we were analyzing that population in Stata, that will look something like this. You never ever drop. I cannot emphasize that enough. So if that was a Stata, you would say so. This is just an example. So we're trying to analyze data, right? In this case, look at prevalence of current smoking just in Alabama. But what we did not do is we did not say keep if states equals Alabama. No, we didn't do that, right? We kept all of their data set together, and then we use a special command that allows us to estimate the mean among adults in Alabama, while estimating the confidence interval of variance among the whole population. So this is what you should do, or something of this nature, if you're analyzing that kind of data that is designed to be representative. In your case, however, since you're using the data that was designed from the world go to only capture results at the level of states, you can go ahead and do this, and that's completely fine. All right, next question.
Okay, let me read one. Some of us seem to be lost. Are we working on examples? Perhaps you need to explain the whole thing again. Someone also asked, in a nutshell, what is the essence of weighting? What would a certain calculated weight mean?
Okay.
What parameters do we classically adjust for? For example, age, religion, ethnicity, etc.
Okay, well, I think somebody in the audience should give us in a nutshell. I think we've explained that nutshell quite a number of times. So somebody who understands, who has followed through what we're saying, should give us what we're saying in a nutshell.
And also, is it the same as setting the quota?
Okay. Yeah, we'll get to that. All right, so who wants to explain to us in a nutshell what weighting is all about? Justice, your hand is up.
Justice wanted to ask a question.
Thank you. Thank you. I wanted to ask a question.
Okay.
But yes, in a nutshell, I think I can comment on the weighting. So, in the nutshell, weighting is a procedure to correct for discrepancies between the sample and the population to ensure that the sample is much representative of the population in order to make correct inferences about the population.
Are you reading from ChatGPT?
No, I'm reading off it.
Oh wow, that was very
Yes.
that's very good.
So if I understand, like you said, we
that was
draw
lovely.
sample from the population.
Yeah.
We draw the sample from the population
Okay.
in order to make inferences from the sample to the population. And there are instances where the sample cannot represent the population. In those cases, you are supposed to ensure that the sample becomes representative of the population. And that's where we apply weighting to ensure that the sample is more related to the population, so that our inferences are more accurate and reliable. Yeah.
I'm very impressed. So that's excellent, you know. So please, so again, right, if you don't understand weighting, that's fine. It's almost it's quite hard to imagine that you're going to just have one session and understand everything about weight. If that's the take-home message, fine, you know. And again, some of you may not even need to use weights, but when you do eventually need to use weight, then you would just know that there's something called weight, and we're going to have other sessions like this, so that drills it in. But this is just meant to be an introduction to weight and to let you know that, well, there's a weighting feature on the Chisquares platform. Should you ever need to do it, you don't have to start worrying yourself, gosh, how do I have to calculate weight, right? It's whole session was just to orient you to weight in general and why we need weight. And so if you gain that much, then the class is a success. And somebody else, the question on quotas. No, weighting is not the same thing as quotas, right? In fact, assignment of quotas is what might lead to us needing to create weights. You assign quotas, you say, okay, we're going to survey 50 people there. That's a very arbitrary choice, right? Well, at the end of, after assigning all these quotas, you end up realizing that when you now tabulate age, sex, race, you find out that the distribution in your sample is quite different from in the population. And then you have to wait. So bottom line, if you take a data set, first of all, just sit down and look at all the demographic variables. So there were questions on how do you know which variables to select? All your demographic variables, tabulate each of them, age, sex, race, income, what all the variables you have, tabulate them, compare them side by side with the population. If one or more do not match significantly, then that means that you have a problem. Now, how do you address that problem? There are many ways to address the problem. You can just analyze your data set and not try to make any inferences to the population, and that's very good too. Or you can be ambitious and say, well, I want to make inferences to the population. Well, in that case, you have to weight the data on those variables that are different in their distribution between your sample and the population. Okay, another question is, you need to drop observations with non-responses in population survey data. Well, if you are trying to weight if you're trying to, if you're not interested in weighted analysis, you can drop anything. This rule only applies when you're using large survey data that has weights and PSUs and stratum. That's that rule there, right? But in other situations where you're not applying weights, you can drop anything you want. This is specifically to weighted analysis. And we're going to have another session, right? Maybe, you know, to focus more on that. And again, like I said, some of you may not need weighted analysis, but it's good to know that things like that exist so that at least you're more educated on them and you can read more on them. And again, I will encourage everybody to go and read up on it if you're interested in understanding the subject. Obviously, it's not, it won't be reasonable to expect you understand everything about weight from one class. So this is just a primer so that you can go up and read up on it and understand it more. Okay. Any other questions, Lungile?
Isaac.
Yeah. Yes. Hello.
Thank you.
Oh, sorry.
Thank you. I perfectly understand what weighting is and how it relates to sampling. And the calculation actually makes sense to me. Thank you very much for the elaborate explanation and all of that. I just want a simple clarification. I asked the question initially, and I hadn't done to a question I asked it initially, which is after the calculation, and you have a particular answer, calculated weight answer. How do you then apply that figure, that answer, in the survey, in making sense of the sample in relation to the population?
Okay. So you now have to apply methods for weighted data, which which we're not covering. So we're going to have a session on that. That answer to that question is going to take us another 1 hour. So what you should know is this, right? Depends on the software you are using. Let's say, what software do you use for your analysis?
I use Excel, and sometimes I use Microsoft 365.
Okay, you cannot use both of them. Both of them are out of the window. You can't use either. When you're analyzing complex data, you have to use a platform that has capacity for weighted analysis.
Okay.
So that's step one, right? So that software could include things like R or Python or Stata or, you know, so you must use the software that has capacity for analyzing survey weights.
Oh, okay.
So and we've had several boot camps on analysis of complex survey data. So maybe we're going to have another session like that. If you are really interested in such analysis, you really want to sign up for those. So again, follow us on LinkedIn so that when we announce that, you will be in the know and sign up. But you know, if you're serious about really accelerating your career in terms of publications, you have to know how to analyze survey data, because there's so much data out there, but most of the data out there are complex surveys. So there's no way you would want to grow fast in your publication outputs that you won't need to understand analysis of complex survey data like the back of your hand. So I would definitely encourage you to follow us and sign up once we announce such sessions.
Okay, that would be interesting. I really have interest in weighted surveys. I do a lot of inferential surveys, and I think weighting is something I need to dive into as well.
Okay, definitely. So yeah, and that's why I said, it's gonna confuse folks the more if we go into that now. So just sign up, just follow us, and when we announce it, you'll be the first to know. But again, this is just high level of what weights are and how we create them.
Okay, all right. I appreciate it.
You're welcome.
Justice, do you still have a question?
Yes, please. Doc, at the beginning of the lecture, you commented on the difference between standardization and weighting. I would be grateful if you can take it briefly again.
Okay. So standardization is when we standardization, simply put, right? We want to compare two populations. If you're not comparing two populations, then there's no point doing standardization. So we only use it when we're trying to compare an indicator between two populations. Let's say COVID incidents. Let's say we're interested in COVID incidents, and we're saying, is COVID incidents higher in Ghana compared to the US? It's like, but you are comparing apples and oranges. Of course, the incidents will be higher in the US. Why? Because the US is an older population, it's an aging population, and people have higher risk factors. So if you want to make a fair comparison, you should have apples to apples. There's a reason why, if we're doing a FIFA World Cup, you want to make sure that both teams that are playing are equally matched. You can't bring under 17 players playing a World Cup tournament because it's not a fair comparison. It's not a fair match. So you have to make sure that likes are compared to likes, apples to apples. So if you're comparing, let's say, COVID incidents between Ghana and the US, you are comparing incidents in an aging population versus that in a much younger population. It is biased, obviously, because the distributions are very different. Standardization is a way of forcing those two populations to be alike, right? So when we do standardization, we create a pseudo population. It's called a pseudo population because that population does not exist in reality. We are forcing America to look like this population and forcing Ghana to look like this population. So we're creating a pseudo population. So the question we're saying, what if Ghana looked like this population? What would the incidence of COVID be? And then what if the US also looked like that same population? What will the incidence be? So that's what we do when we're doing standardization. With weighting is the same, it's a different thing. With weighting, we're not comparing two things per se that are different. We're comparing a sample that came from one population to that parent population. We're trying to make sure that that sample looks like the parent. So the difference is essentially is that in standardization, it's two different things we're comparing. In weighting, we're comparing a parent and a child. And we want to make sure that child looks like a parent, right? Standardization is comparing two strangers. This is comparing a parent and a child. I want to make sure that that child looks like the parent. If the child doesn't look like a parent, then we have to weight the child so that it looks like a parent, so that we can make inferences from a child to the parent. I hope that answers your question. Okay, well, assume it does. Any other question, Ungile?
Ogunboye.
Yes, please. Thank you, Doc.
Yeah, I just want to confirm the time for the Tuesday's Python class. Thank you.
Same time, 12.
Okay, that is no, Dr. Gakwe, not same time. It's at 4 p.m. The time is on the chat box. If you can check, I've just posted the links, registration links for all the sessions. So the Tuesdays, that is 4 p.m. West African time, 5 p.m. South African Standard Time, 6 p.m. East African time. If you're in Ghana or UK, it's 3 p.m. Thanks.
Thank you.
Right. If a study is on companies, say for African companies, for African countries' finances, what should we do? Standardization or weighting? Can the use of dollar to translate their currencies standardization? Rosemary, Doctor, would you like to ask that question verbally? Otherwise, Dr. Gakwe, I'm not sure if you heard. I'll read again.
Okay, please read again.
Okay. If a study is on companies, say for African companies' finances, what should we do? Standardization or weighting? Can the use of dollar to translate their currencies, question mark, standardization, question mark?
Please, we have to learn the art of fleshing out, asking real coherent questions, because if they're not full-fleshed, I can't read your mind to answer the question. So I'm going to answer just the first part.
Okay, she's unmuted herself.
Okay.
I think she's going to ask.
Okay.
Okay, thank you so much for the opportunity and thanks for the rich lecture. I'm asking if one is conducting a research that is comparing the finances or financial variables of, let's say, 4 African countries. Obviously, they have different characteristics. So what should we do? Should we standardize or is weighting that is required? That's what I'm asking.
So so you have 4 companies. You are taking all their finance records, right? For the 4 companies.
Several companies from 4 different African countries.
Yeah, okay. So you have
Yeah.
you take, let's say you're interested in companies that manufacture cement. So you take, in each country, you take all the financial records for each company, right?
Yes.
And so all the financial records for all the cement companies in the 4 countries.
Yeah.
In this case, so do you think that, do you have a sample or do you have a census from the scenario you have?
Okay. I think we worked with those listed on the public their stock exchanges.
Yeah, but
I think that's the population now.
Yeah, so what you have is the population. That's the point I'm trying to drive at.
Yes.
So do you think you need to weight the data?
No.
No, you don't. Now, regarding your other question, do you need to standardize? Are you interested in the actual population or are you interested in the pseudo population? Remember, a pseudo population is a fake population that does not exist.
Okay.
Are
Is
you
it the same as target population? Pseudo population, is it the same as target population?
Pseudo means fake, false, something that is
Fake.
made
Okay.
up.
That looks like.
So are you interested in a made up population or the actual population?
Well, it's the actual population we're interested in.
Yeah. So given that standardization just creates a dummy, a fake stuff just for statistical accuracy or issues of fairness in comparison. But you are interested in the real thing, aren't you?
Yeah.
So do you think you should standardize?
Well, maybe what's coming to my head, I'm looking at it from currency perspective. Because when we talk of their financials, Nigeria currency is Naira, Ghana is CD and all that. So how do we, I'm sure you are with me now.
Okay, I do. So that is, okay, that's one form of standardization that is so that is also standardization, but it's different from this kind of
what we are discussing.
Exactly.
Okay.
So in that case, you can standardize the dollar, the currencies, right? So that you're working with a fixed currency and you're not comparing apples to oranges. So you can standardize the currencies to the dollar, and so that's fine. But in this case, we're talking more about population level indicators.
Population. Okay.
But that
Thank
is
you so
also
much.
standardization. But that's currency standardization. Here, it's talking about standardizing population.
Okay. Thank you so much. I appreciate it. Yeah, thanks. I appreciate it. Yeah.
Yao.
All right. Thank you so much, Doc. I really appreciate this session. It's been really informative. So my question is around the whole idea of this standardization and weighting. I think I understand the standardization very well, but the weighting, I just want to understand what exactly is happening when you apply. I get the design weighting. I know that you can take care of that at the design stage, where you sample individual according to the size of their size in the population. But what I don't quite understand is when you come to the non-response, weighting. So what exactly is happening in the background? When you, for example, when you weight your data according to, say, age, and you have male and female, say 60% of male responded and 40% of female responded. But in the population size, you have it in the other way around. That's 60% female and 40% male. So when you apply that during the weighting, non-response weighting, what exactly are you creating? What is happening in the background? Is it like we are now changing the response from the one that over-responded, so that you can equate it in a way that it will match the size of that the individual, gender in the population? Or what exactly is actually happening? That's what I don't really quite understand. I don't know if you got my question.
I did, yeah. So it's more of like the methodology. What's the methodology that is taking place in the background?
Yes.
So here, right, in this case, right, we have this is a case where the proportions or the distribution is overrepresented in the sample. What is happening in the background is that it is not, so just to be very clear, it is not changing the value of whatever the people answered. That nothing is changed in the data set. What we are doing is creating a weight variable, right? In our data sets. And again, the best way to do this is to practice. So if you have a survey, you can practice playing with this on the Chisquares platform and seeing what happens. Unfortunately, I don't have a survey that I can use, but again, the best way to learn is to practice over and over. So what it does is that in the weight variable, these people who have a larger cover are given a smaller weight. These guys with a small cover are given a bigger weight. So that when you now apply the weight in the analysis, the distribution for gender will now be similar to what you have in the parent population. The weight will correct for all of those inadequacies, right? So again, remember we said this is the whole process of weighting. It is essentially a process where we force the sample. This is how the sample look like. This is how the sample is looking. We force it to take the shape of the parent population. Conceptually, that's what's happening in the background. That's what the computer is doing. It's using those variables and adjusting for and calibrating. That's why it's also called calibration, right? It's recalibrating the distributions so that at the end of the day, the shape of the population of a sample is changed from this to this. Now, remember that the amazing thing about the weight is that it's not doing that just on one variable. And this is the beauty of Raking or of iterative proportional fitting. It's doing that on all the variables. And so what it does is that, let's say you have 30 variables to weight on. It takes the first variable, and that's why we call it iterative. It takes the first variable, applies only that first variable to the whole population and creates a weight for the whole population with that first variable, right? Then the application you're using or the computer program takes that weight variable again and looks at the distribution of that characteristics like age with that weight, right? And then it applies the next weight onto that first one. And then it repeats the process over and over and over until it has corrected for all the variables. So it's not as if it's just taking all the variables and cramming them together to create a weight at the same time. It does it iteratively. That's why we call it iterative proportional fitting. Each of those words has meaning. Iterative meaning that it's done one after the other. Proportional meaning that the whole point of modeling, and again, all of this thing is modeling, right? Modeling is when we are trying to simulate reality. In this case, we are fitting mathematical models in the background to see whether the distributions are proportional to the parent population. And it's done iteratively. So take the first variable, we apply it, then we take a second variable, we superimpose it on the first one, then we take the third one, we superimpose it on the first and second, and we'll do that until we've applied all the variables so that at the end of the day, our mathematical models have accounted for all the weight variables in such a way that we have now forced this sample to look like the parent population in a way that it's, of course, it's still a pseudo population, but it kind of resembles the parent population more. Does that answer your question? Okay, well, I assume it does. So if you guys don't get it, it's understandable. Like it's quite an abstract topic, but again, maybe when we have another session, you would understand better. But again, if you're interested in research, and for those of you who are interested in the business of research, you need to understand weight like the back of your hand. There is no large complex survey you would do that you will not have to worry about weight. So if you're interested in making a career, like running the, research as business at the highest levels, you have to know every single thing about weight, like the back of your hand, right? If you're just interested, so it depends on what your career aspirations are too. You may not have to worry about it if you're just interested in small data sets or just your day-to-day research projects. But for those who have, if you are interested in more understanding what happens in the background, understanding not just how to use weights, but how to calculate them. If you're interested in the career of the business of research, like making, doing studies for large companies or governments or national entities, well, you have to know weights, everything about weights, so the level of knowledge required or desired may just vary based on what you want to do and what you want to use the knowledge for. But yeah, I see your hand up. Let's see, who's this? Muhammad
Usman.
Okay, thank you very much, sir. Well done. We really appreciate you very well. There was a time I joined lately, but I had you giving an explanation about what weight means to an ordinary person. I think it makes sense. I don't know if you can help me repeat the explanation, sir, because I joined you in the midst of the explanation and I found it very interesting because I think it will help for someone to understand what weight means to a lay and ordinary person, sir.
So what did you understand from what you met? What did you hear? Let's start from that.
So I joined very late, sir. So that is why I'm just. But when we could, because I normally like things, bringing things down to the ordinary person's or layman's understanding. Because I think once you pick things from there, then you will understand this, things better.
Okay. So who wants to volunteer to explain to him in a lay manner what we said? I believe you're referring to the slide here. Let me see if I can find it. Let's do that way around. So we need a volunteer to explain to Usman what we meant, or since he joined late. And Usman, try not to join late next time.
Anthony, would you like to give it a try and then answer and then ask your question?
It's the question I want to ask.
Wait, can I attempt?
Okay.
Can I attempt?
Yes, you can.
Okay. So basically, it means that you are trying to relate a sample proportionately to the population in such a way that each aspect of a given population is represented appropriately.
Okay. So let's take the first guy, for example. That's a weight of 4. What does that mean in lay terms?
Okay, so the weight of 4 means that in lay terms is that the individual is derived from 4 entities overall.
Okay. Any other? Give me, what do you mean derived from? That's the part of your answer that is kind of sketchy.
So it's like saying that there are 4 units overall for a weight of 4.
Okay. Okay, let's get it.
Versus, for instance, if there are about 100 units. So let's say the units represent particular demography, so to say. And all of them put together amounts to 4.
Okay, let's get the different opinion before I come weigh in. Enduro path.
So I think the trick here is to explain to a very lay person.
Okay, thank you. I want to appreciate you for the lecture so far. My name is Enduro. In a layman way, the best of how I understand it is that maybe in a sample size of a population of 100, and you've been able to take sample maybe of 20 samples from the 100, and particular order that out of that 20, each of the sample is carrying perhaps 4 persons that representing the whole. So by the time you put the 4 of each, which is, or 5 as the case may be, of each, by the time you multiply it, you will now amount to the totality of the population. So that's the way I understand it. Okay. So now each person is now carrying what each one person should be carrying in the whole population. So now the 20 will now be representing the exact of 100 as a population. So that's the way I understand it.
All right, thanks. Now, Now, I just want a simple explanation that does not include any other numbers, right? Row number 2 is 4. So what does just that 4 mean without introducing any other number? What does that 4 mean? Maybe somebody else. Ogunboye, your hand is up.
So what that 4 means is that individual in the sample is representing 4 people in the population, including himself.
Exactly. So that's what weight means, essentially, right? So if that's all you get from this sample lecture today, that's fine, because the use case might not be very relevant to what you're doing. But again, whenever you come into a scenario where you need to use weight, well, the goal is that you know what that means, and you know how to at least have an idea of how to go about calculating it on the Chi-Squares platform. Any other questions?
Anthony.
Good afternoon, Prof. Good afternoon, everybody.
Hello.
My question is on your screen now. There are different columns on the screen as I'm looking at it. One represents the weight, and then another column. Then, if I look at this, there are different weights on the screen. I think from what is up to 38 different weights, values for weights. Now, to get these values, is there a standard formula? Because when you talked about standardization, there is confidence interval and there's level of significance. And all these ones, they have formulae to calculate them. Is there any formula to calculate this from either the sample or from the entire population? That's my question.
Okay, so we just walked through the Chi-Squares platform to show you how that is done. So we said that you would come to your survey. You don't do it. So first of all, you don't do this thing manually, right? It's done with software. And on the Chi-Squares platform, we've provided an opportunity for you to do that. And so you first of all have to close the survey. Step number 1, you close your survey. Step number 2, you come to data access and insights. You click on weight data. Step number 3, you select the variables that you're going to use to create the calibration weights. So let's say these are the variables, the 2 variables or 3 variables you want to use. You select them. Step number 4, you go to the census data or whatever source of data you're going to use, and you get the distribution of that same variable in the national population or in the target population. So that could be 20 and whatever the percentages are, right? You provide those percentages in here. When you're done with a variable, you say you're done with this variable. And you go to the next variable. You select that to 20 and 30% and 10% and 20%. Whatever, I'm just obviously just making up these numbers, but whatever the distributions in the populations are, you provide them accordingly. Must add up to 100. So they must add up to 100. So 20. And you do that for all of the variables that you're trying to weight the data on. So 25, 25. Right. You cannot have missing values in those variables that you had. They all must have values in observation. This is a very poor example because this is not a data set that has demographic variables. This is just an evaluation course in evaluation survey. So it's not the most fitting example. But once you are done, you click on generate weights. And so what the platform does is that it applies calibration weights. Right? See, say success, new calibration weight created. So this is the time it was created. This is the variables that were used for the weighting. The status is success. The number of variable is weight var. If I download my data sets, then I would have a variable called weight in that data set. So this is my data set that I just downloaded from the platform. I can now look for weight var in that well, so it's good. So again, like I will encourage you, just practice this, right? You can, after this class, go through this process of, I'm not sure if you have data sets, if you have set up a survey yet, but just go through the whole process, create weights. It is by practicing that it will now start to make sense to you, right? And then when you're done, you can now examine the data set to see how this variable looks like in your, and then you can also look at the distributions. There are the actions here for you can compute the benchmark, you can view the summary of the weights. You can, so for example, this is calibration weights. This tells me that the minimum value of this weight var is 0.0255. The maximum is 28.25, right? And the median is 0.3142. This is for the weight we just created. I can trim the weights. We trim weights when weights are very variable. But again, you got to practice this, right? So this is just to show you that, one, the functionality exists on the platform for you to implement Raking on the platform. But the best way to learn is to practice over and over and to see how that, how that works out. Any other question?
Thank you very much, Prof.
Dr. Sharon.
Sorry, let me just
I have, okay. I always say this, is it software specific or case specific?
Everything is contextual. It depends on it depends on what you're trying to adjust for. So you are the one doing the research. You are the one who has the data set. You're the one who knows the variables that are in the data set. So yes, it's context specific, it's service specific, it's research, so I hope that makes sense.
It's clear. It's clear.
Okay. These variables here are just dummy variables. Like in your data set, you're going to be looking at actual demographic variables like age and sex and race and all of that. And that's what you're going to use to create the variables. So that when you're now analyzing your data, you're going to analyze it and use this variable, this weight var, and you can change the name to anything you want, but that would then be incorporated into your analysis. I think the problem is that most of us in the audience are not familiar with analysis of weighted data, so it's a bit abstract. I think that is the problem. I think that's my suspicion, at least, that most of us in attendance are completely unfamiliar with how complex data are analyzed. So maybe that's one of the things we have to cover for you to now get an appreciation for what weights are and how we use them.
Thank you, Prof.
Welcome.
Dr. Sharon.
Yeah, thank you very much, Professor Agagu, for the efforts to bring us to this level of understanding. Like you said, it's abstract, but I think after this lecture, it's not as abstract as it was before we came. Please, I have two quick questions. When you talked about getting the percentage in target population, and you referred to the fact that there are data, especially in America. Now, when you're in a situation where you don't really have data, how do you get this target population, the percentage in target population for your calculation? That's one. Then the second question is, I just want you to confirm or maybe explain otherwise. Now, does this weighting, does it minimize sampling bias or errors such that your data becomes more generalizable? Is that what weighting is trying to do? Minimizing?
Yes.
Okay.
That's the whole point of weighting. Weighting is to make our data more generalizable. That's why we emphasize the cycle of inference. Sample from population to sample, from sample to population. And the goal is to make that cycle go round and round. So the whole point of weighting is to make our data representative, or at least more representative. It's not going to solve all our problems, but at least it's going to make it more representative.
Okay.
Does that answer that part of your question?
Yes.
Okay. The first part was, so where do you get the data from? Well, you go to Census Bureau, Census Bureau Nigeria. I'm not sure what it's called. Nigeria or Nigerian. Okay. So here we have Nigeria Census Bureau tables. You can search for what is the statistical agency in Nigeria called? Nigerian Population Commission. You can look at the every country has data, right? You just have to search. So you have to search and figure that out, and So for example, I'm more familiar with Statistics South Africa, let's see if I can find something there. So every country in the world would have demographic tables. So that's a big part of the whole problem, the whole question, right? You have to do the work of finding out what those numbers are. So again, for those of you who ever go into the business of research, you will have government agencies of countries that will say, oh, we did a survey and it's not representative and we want to make it more representative. It's your job. The hardest part of this, your job now, is to go out and actually find the estimates that you're going to use to calibrate your data against. That, if you have done that part well, that's the hard part of the work. The remaining part is just plugging in those numbers into the Chi-Squares platform and getting your weights. But so my point is that you have to search a lot. Sometimes you might have to get one data from one point and another from another point. So it's not all going to sit now one place for you to nicely just come and plug them. You have to put in some work. Sometimes you might look at, so for example, Nigeria, right? If I were to weight data from Nigeria, I might say, okay, is there any national survey that is representative of Nigeria? And yes, there are. There is a National Adult Tobacco Survey. There is maybe a couple of other surveys, right? I can then use those surveys to see, okay, nationally, that this is, even if I don't have census data, you have to think outside the box. You can say already, based from this national data, I can see that the distributions of gender are 50% male, 51%, or 51% male, or 49% female, right? Those are now the benchmarks I'm going to use to calibrate. Those are the population marginals. I'm now going to take those numbers and take them to the platform and then use and input them for gender. Now, maybe that survey doesn't have data on religion. So I may have to go and look for religion elsewhere. Maybe the National Association or National Bureau for Religion Studies in Nigeria says that 21% are Muslims and 40% are Christians and the rest. Well, I get that data from there. So you may, ideally, you'll find all the data in one place by the census, but no, in a real life, oh, you have to do a little more digging to find all the data you need.
Wow.
Does that make sense?
Very well. Thank you very much. Thank you.
Great. But again, for those who are interested in a career in the business of research, there are some fundamental building blocks foundational things you have to learn. Oh, the very first of those is, weight. Because how do you design a large national survey for any entity, whether that's a corporation or a government, without knowing about weights? It's required knowledge. So I can't emphasize that enough.
Okay, Isaac.
Yes. So, Prof, basically what all of this weight thing means is that it helps you is representative of population, or how a population can then be used to actually arrive at a given sample. Am I correct?
Yeah, this is the whole point of weighting, is this part here. How do we make inference from sample to the population in a way that it's truly generalizable? Yeah, so that's the whole point.
Yes. Okay, so away from that, I understand that part. I'm waiting for the lecture on how to make sense of weight score. I'm very interested in that.
Okay. So
yeah, the other.
Okay.
Sorry, go on. Sorry, go
no,
on.
So I was just saying that make sure you follow us on LinkedIn so that when we announce it, you would be in the know.
Okay. So the other part is a little bit away from the lecture for today. I've tried severally to log in, reset my password. It's not working. Is there something I need to do?
You can declare your password as lost and try to get a recover password.
Oh, okay. Thank you very much.
Welcome.
Okay.
Yao. I don't know how you pronounce your surname. Yao.
Hi.
Yao.
Yeah, you're right. The first pronunciation. Yeah. All right. So thank you, Prof. Mine is just a comment. I think you rightly mentioned that most of the participants appear not to have an experience of analyzing weighted data. So what I just want to recommend is maybe in the next session, the next class, maybe we should look at the analysis and also the interpretation of weighted data. I think that will really be a value add to this class, so that everyone can now be able to not just calculate your weights as relates to the data set, and also be able to analyze it and interpret it in the right way. So I just want to recommend that maybe we should incorporate that into our next class.
Yeah, so we're gonna have a session for that for sure. Now it may not necessarily be the next class because I think we have a schedule of events. So, but when we let's see what the schedule for next week is. But when we have at the end of this session of this series, we can definitely have. So next week we're supposed to have electronic data. So we're following this schedule religiously. So what that means is that at the end of this session, we will just need to have a separate session on analysis of weights. But so we stay true with the schedule. We will stick with this, and then when we're done, we'll have that session for folks who are interested. But we have a manual that will also share a step-by-step manual on analysis of complex data. We're going to share that with you. Let's see if I can figure that out. Let me see if I can find that and share that right now. So this is a manual that describes step-by-step guide to analysis of complex survey data in R, analysis of weights. Again, it's really, really simplified. We wrote this manual so that anybody can just follow it. Step one is so explicit. Step one, do this. Step two, do this. So this is a resource that you can follow. So let me just share this so that folks who are interested can start learning on their own. So this is a manual if I can, where's the stuff? So the instructions in the manual are pretty explicit so that you can self-learn. So that is it here. And we have another manual in Stata, I believe. Let's see if I can find that. Stata, we're going to write another one in Python and in SPSS and also in epinfo so that folks can follow. But yes, you'll have to just for now self-learn. So those are the things you need to figure it out on your own. All right, any other questions? Well, we're all set.
Wisdom.
Sorry, Professor Kago, I just clicked on the second link. It's saying you need access, like you can't just log in.
Oh, really? Okay.
Yeah.
Okay, let me change the settings. Just a minute. Thanks for that. Thanks for letting me on that. Oh, sorry, it's restricted. Anyone with the link can view. All right. Done. Let me do that for the other one too. But again, if you really want to increase your publication, and you have to learn survey data analysis, like complex surveys, because there's just so much data in the world, but most of it is complex data. So if you had that, you can literally publish one paper every week if you wanted, because there's that much data in the world. So when people are fighting about publications, it doesn't make sense. Like, why there is so much data in the world? Why are you fighting over data, over publications? All right, so I've unlocked both of them so that everybody can access.
Thank you very much.
You're welcome.
All right, thank you. Thank you so much, Professor. Prof, this is Wisdom Aquari speaking.
Yes.
All right, thank you so much. It's been a wonderful time, and I must really say, God bless you for giving us this opportunity to learn under your tutelage. Since this lecture started, honestly speaking, I have gained a lot. I'm just trying to say concerning what we posted on the Zoom platform right now, the step-by-step. When this Zoom link, when the meeting finishes, we will not be able to have access to it. So I'm saying that we can post it to our WhatsApp platform.
Okay.
So we can copy it and put somewhere.
Okay.
That's mine.
All right, we'll do that.
Thank you so much, sir.
You're welcome, yes.
Thank you.
All right, Lungile, are we all set?
Yeah, there is another question. Can I know how to calculate weight using the probability method?
Everything is probability. So what do you mean probability? Okay, are you referring to the base weight? Oh, okay. I think I understand what you mean. So you're saying, okay, when you have base weights and you've calculated the probabilities, so the weights are simply the inverse. Inverse means 1 over whatever. So you take the probability and you divide it by 1, and that's the weight. Now, if you have base weight and non-response weights together, you can only have one weight in your analysis. So you have to multiply the two weights together to give you the final weight. And that's why every single, if you look at any data sets, any complex data, the weight final variable is always called something along the lines of final weight. Like this one, this is fin weight or final weight, because almost every data weight you see in any data set is a combination of more than 2 weights. And the way they created that final weight is that they multiplied all the weights together to give you that final weight. That's why it's called final weight. So again, from a probability, you take the inverse of that probability, that gives you the weight. And if you have multiple weights, you multiply them all together, that gives you the final weight. All right. I assume there's no more question. And yes, there's a WhatsApp group for those who are asking. I'm sure
We've been posting links. So let me post it again. But can I just ask that you also try to scroll up to help us, so that those are the links we've been sharing. So we have the evaluation or attendance. Basically, it's one thing. So we will get your attendance. We will capture your attendance if you complete the survey, especially just your name and email address. That's what we use. And we would like to get your feedback regarding the session. How did you find it? So there are questions there that you can respond to. I've posted our LinkedIn link to our LinkedIn page. So if you can follow us, so you can stay updated on our upcoming courses, that will be great. That's the WhatsApp link. I've been sharing it. So please use it instead of sharing your numbers. We have YouTube. I've posted the YouTube link as well. So for all our previous sessions, because this is not the first, it's not the last, we'll have many more. So for all our previous sessions, you can just catch them on YouTube, including this current one. So if you're one of those who have been asking for the recording, just head over to YouTube. You will find this current session that we have. We are there live right now. So it will be saved there for future reference. I've also posted our access links. Those who do not have access to Chisquares, to the Chisquares platform, there are 2 links that I've been sharing. So one is for those who are not in Nigeria, who are not part of the Nigerian institutions. That's the one that says for individuals. So for individuals, and then there's another one for institutional access. Please, if you've ever used the links before, if you were one of those who've been with us, if you're one of those who've been with us since the beginning of the year, we've been sharing this access link. You do not need to activate again. So you don't need to use any of these links again, because that will just create some problems for you. So rather, if you've never opened Victor, I was just asking you that you please use the link, the WhatsApp link, so that we don't have to add people individually. So I've just shared a WhatsApp link. Please click on that, and that you'll just be able to join the WhatsApp group. Abishoya, you have a question? No, Tricia, use the WhatsApp link that I've just shared. Please don't share
Hello,
numbers
can you
here.
hear me?
Yes, we can hear you.
Okay, all right. Thank you very much. Thank you, Prof. Again and again. I actually posted the question on the chat box. I wanted to find out how to apply this weighting when you are doing a vaccination coverage and you have to do maybe multi-stage sampling. And then how does it come in, please?
So multi-stage sampling means that you have several stages in sampling. Let's stick with the example we used earlier. Where we said you have let's say you are trying to do a survey of students in the Kingdom of Saudi Arabia or in Nigeria. Let's use Nigeria. And in the first stage, you selected schools. Second stage, you selected classes in those schools. And then the third stage, you selected students in those classes. So that's a 3-stage sampling technique. Schools, classes, and then the individual student. So you have can we can limit ourselves?
So she's at the junction there.
Michael, can you limit yourself? All right, so we have a 3-stage cluster sampling. First stage, we selected schools. Of the many schools, we selected some. Then within those schools, we selected classes. Then within those classes, we selected the students. So we have to first stage is that first step, we have to calculate the probabilities at each stage. What is the probability of selecting schools? Of all the schools that were selected, we calculate the probability for each school. Then what's the probability of selecting the classes within each of those schools, right? We select for each class, we calculate its probability. And then thirdly, what's the probability of selecting the students within each class? So we have 3 probabilities that we've calculated at each stage. So that means that we have to calculate the final probability of selection for the 3 stages, which is the probability of being selected in schools times the probability of a class times probability of individuals. That gives you the final probability of an individual being selected. Because remember that for an individual being selected in the survey, is selected conditional on their class being selected, which is conditional on their school being selected. So the product of those 3 probabilities gives you the final probability of selection for a given individual. The weight for a given individual will be the inverse of that product. So if the probability of selection was 0.5, the weight will be 1 over 0.5, which is 2. So different students will have different weights because that reflects the different probabilities they had of being selected in the classes and being selected in the schools, right? So that is what you will do to calculate the base weight. So you now have your base weight. You can then go and calculate your non-response weight, and then the final weight will be the product of those 2 weights together. So that's how you would that's how you calculate the weight, the final weight for that survey. And yes, this is a multi-stage sampling because there are multiple stages. The first stage 1, we selected schools. Stage 2, we selected classes. Stage 3, we selected individuals in the classes. Okay, I believe we've answered all the questions. If there's any question we've not answered, you can just unmute yourself and ask.
I think it's best to raise their hands, Dr. Gaku, because
Okay.
then it becomes chaotic.
Okay, that's fine too. All right, speak now, forever hold your peace. Okay, all right, thanks everyone. I believe there are no further questions. It was great having you in class, and I guess we'll see you shortly. Any other questions, you can feel free to direct them to Lungile.